C-Therm's purpose is to simplify thermal conductivity testing for the materials of tomorrow. Since 2007, we have emerged as the global leader in test instrumentation. Our core strength in thermal conductivity is built on now industry-standard Trident instrument and broadened through strategic partnerships with Rigaku and Metrovid, providing one of the most dynamic portfolios in thermal and mechanical analysis.
Thermal conductivity describes a material's ability to transfer heat energy through conduction. In electronics, whether you're developing a smartphone, aircraft, or electric vehicle battery pack, the thermal conductivity of the materials is a major factor in the overall thermal management of the device. In other applications, like metal hydrides that are used as hydrogen storage media in fuel cells, the thermal conductivity impacts the kinetics of hydrogen adsorption.
The most common mistake we see in industry is applying a good method of measurement on the wrong type of sample. This is what happens when you're limited to a single tool and are facing a variety of sample formats. The Trident was designed to provide researchers with multiple options on a single instrument platform, so you always have the right tool for the job. It's been a huge success. Leaders like NASA, Adidas, Intel, Kimberly-Clark, Lucid Motors, and universities around the world choose C-Therm analysis tools and the support we provide.
C-Therm customers get access to the most advanced transient methods and are able to test under real-world application conditions, including humidity, temperature, or pressure. C-Therm's patented MTPS single-sided sensor is the fastest and easiest way to measure thermal conductivity. The Flex TPS is brilliant for more challenging applications and testing anisotropic and thin film samples. Our needle probe offers robustness for polymer melts. And the new THW is great for low viscosity fluids like engine coolants.
Not every client's ready to bring testing in-house, so we also offer industry-leading testing services here at Thermal Analysis Labs. C-Therm's highly skilled and experienced team provides access to the most advanced characterization tools for thermal properties and the expertise to make sense of the test results. For example, Rigaku's breakthrough sample observation capabilities allow users to video record a sample as it undergoes a heating cycle. When working with an unfamiliar material, you can see phase changes, crystallization, and other phenomena. This is vital for understanding the material and helping tell the story of how it behaves.
Metrovib's line of DMA offers the broadest frequency range and the highest force available on the market. This is just one of the reasons it is the standard in the rubber and tire industry. We work with a lot of folk developing different fillers for tires, including carbon black. And due to its sensitivity, the DMA is by far the best method to measure the glass transition point.
C-Therm aims to help accelerate material research and improve outcomes driven by better material performance data. Let us help you get the best possible data for your research, simplifying thermal conductivity.
Right. Good day, folks. We'll be getting started here with the webinar in just a couple minutes. Few housekeeping items to go over before we jump into it here today. Today's session will be recorded and available for playback at the end of the session. If for some reason you had to jump off earlier, maybe there are some colleagues that weren't able to make the live time, you will be able to share or pick up on the webinar at a later date. It should be posted within 24 hours of the live session. For the folks on the line with us, I will make note of the Q&A feature. So in the bottom right corner, there's a little Q&A icon. Throughout the session, if you do have any questions related to maybe some of the content being presented or maybe something related to work that you're doing, you just wanted to have a chat about it, we will reserve some time at the end to go over all the questions together. If you're interested and you have some questions, please feel free to stick around at the end. All questions will be answered at the end, not throughout the presentation itself. All right, so that being said, a couple minutes past the hour, we'll go ahead and start. From my side, my name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies, and I'm welcome everyone here to today's webinar. Today, we're taking a look at the thermal management of tires to improve heat resistance, and it's a special webinar. We do have a guest speaker, Nikki Hirschberger, VP of Technical Consulting at ARDL, who will be joining us here shortly to take us through the bulk of today's session. Before I pass it over to Nikki, though, just going to do a quick little intro to C-Therm, who we are and what we do. For those that may be new to us, I want to give you a little background. So C-Therm, we focus on the measurement of thermal conductivity, specifically using the transient class of measurement technique. We'll give a little bit of background on how this is done and, of course, how it relates to today's topic. But with that being said, I do want to introduce our core instrument platform, which is called Trident. So you can see a picture of it here. Trident is a modular system. It brings together 4 different methods for the measurement of thermal conductivity, again, all under the transient class of measurement technique. Ultimately, depending on maybe the sample type, the sample size, or the conditions that you're looking to test under, this can dictate which a method is most appropriate. And the idea behind Trident, kind of the inspiration, this quote here from Abraham Maslow, we like to reference it: when all you have is a hammer, everything looks like a nail. So again, this idea relates to if you only have one option for how you're going to measure something, you may be trying to, fit something that really isn't designed for that specific method. So again, with Trident, it gives you that more of a toolbox approach to be able to best pick the device or the method for the task at hand. Today I just wanted to give a little bit of an intro on one of these methods in particular, as it will be featured in some of the later content, the MTPS, or Modified Transient Plane Source. You can see a picture of the sensor on screen here. This is C-Therm's patented single-sided sensor design. The active area, just to give you an idea on size here and scale, if you've never used this device before, it's about 18 millimeters in diameter. So, one of the big requirements here is that for your material to be able to take a measurement, we have to at least be able to cover that active zone. But again, quite a small surface is needed. Now, a typical setup could look something as simple as this. You have your sample with a little weight on top to ensure contact. The thickness requirement does vary depending on the type of material. Generally speaking, just a few millimeters is what is needed for most, in the sense of today's topic, talking about like polymers, rubbers. So you get away with quite a small sample size. And of course, maybe not the most large focus of today's talk, but I do want to make reference to that the MTPS itself can also test a variety of non-solid materials. There's a very simple setup for this. There's an attachment called the liquids and powder cell. It fits right over top of the sensor. And then, of course, that can contain your liquids, powders, pastes, whatever that may be. So won't go too deep into the theory, but again, just to kind of set the groundwork here, the idea behind the MTPS measurement, somewhat similar for many transient techniques, is that the sensor itself is acting as a heat source. So this heat source is going to deliver the thermal input to the system for measurement. We are monitoring that change in temperature that occurs as a function of time. And the thermal conductivity is inversely proportional to that temperature rise that occurs. With the MTPS, all of this analysis, all the measurement is done automatically within the software based on the calibration that is selected. This is one of the reasons why it is one of the more easier and, let's say, simpler methods to get set up and running with, while still providing quite a nice bit of information on the thermal properties of the material. So when we talk about the MTPS at a very high level, it's going to be one of the go-to methods that groups will typically approach for, rapid feedback on a variety of materials, especially useful in like an R&D capacity. As I mentioned, being able to test solids, non-solids in a variety of formats, quite flexible. And not something that we'll go into here today, but the thermal mapping aspect, there's a really unique capability here of the MTPS to assess the essentially verification of the dispersion of the fillers within the material. So there's a nice application use case there as well. So we won't go into all of that here today. I will just make note of our method selection guide. This was recently updated the other month, so it's got a lot of new information, really highlighting all of the capabilities on Trident, maybe some more application-focused examples in there as well, a little bit of elaboration on the theory, but also talks about a variety of other methods that exist in industry. So again, for folks on the line that maybe you're newer to the space of thermal conductivity, or maybe you're just looking for a nice little refresher on some of the options that exist out there, this is a great resource to take a look at if you haven't already done so. But with that being said, that kind of ends my little intro here. And it's at this point, I'd like to welcome Nikki on screen to take us through the remainder of today's session. So thank you, Nikki.
All right, good afternoon, everybody. My name is Nikki Hirschberger. It's very nice to have all of you here today for this webinar. So I actually work for Akron Rubber Development Laboratories, and today what I am going to talk about is the thermal management of tires to improve heat resistance and to prevent premature wear. So I just turned the video on for a minute so everybody can kind of see me, see who I am, but I find it easier to have the video off when I'm actually going through presentations because it'll help you guys focus on the actual slides themselves. So getting started today, first of all, let's go through the presentation outline. So first, we're going to talk about the introduction to heat buildup in tires. Then we're going to talk about factors influencing heat resistance. Then we're going to talk about the theory behind heat dissipation. And then we're going to talk about fillers that actually promote heat dissipation, and they do this through thermal conductivity. So then we're going to look at a study that we did. And what we did is we replaced low levels of silica with thermally conductive fillers in a passenger tire tread formulation, and then evaluated them for wear and aging properties. And we'll go through some of that data. So first of all, what is heat buildup in tires? So tires generate heat due to hysteresis, and hysteresis is the energy lost during cyclic deformation as they roll. And heat generation causes multiple issues. One, it increases the rolling resistance, which means you're going to have worse fuel economy. It promotes premature aging, and it also reduces your abrasion resistance. And for years, people have talked extensively about rolling resistance and how that translates back to heat generation and hysteresis. And we wanted to kind of focus on some other things. So we're going to focus more on premature aging and reduced abrasion resistance. And these are really important. And premature aging, when you start talking about a tire, this happens for two basic reasons. The first one comes down to polymer type. So when you're talking about a tire tread, the normal polymers that are going to be used are a solution SVR, natural rubber, or polybutadiene. And if you think about these thermoset polymers, if you think about them from like a heat age standpoint, they have the worst heat resistance of all of the thermoset polymers. So that's one of the reasons why you have premature aging. The second reason is it comes down to the cross-link types or the cure system that you're actually picking. So if you think about a tire and think about the tread itself, you want something that's very strong, very durable, that's going to have higher cross-link density. However, on the flip side, it has to have good flex resistance. And flex resistance actually goes to lower cross-link density or lower bond energy. And the way you do that is you increase your polysulfidic crosslinks. And polysulfidic crosslinks, of all the crosslink types, when you're talking about thermoset polymers, it has the lowest bond energy, which means they're the weakest. This is why flex is very good when you have polysulfidic crosslinks. However, when you have that lower bond energy and you have lower cross-link density, you're going to be more prone to aging and different things like that because the cross-link structure just isn't that tight or that strong. And when you have premature aging, when you're talking about the types of polymers used in the tire tread, when they age, most of the times they soften. And if they soften, you're going to have reduced abrasion resistance. So this is why heat buildup and hysteresis is bad for a tire tread application. And like I said, we're going to focus on the aging and abrasion resistance. So let's talk about heat resistance. And first of all, we're going to talk about thermal stability. And when we're talking about thermal stability, we're talking about when a rubber product, thermal stability of a rubber product is important because exposure to heat over time causes thermal degradation that leads to molecular deterioration of the polymer that can result in softening or hardening depending on the polymer. Think of thermal stability as a chemical mechanism. So the things that are going to influence this are the types of the base polymer that you pick, your anti-degradant package, or if you even use an anti-degradant package. And then, as I mentioned on the last slide, the cross-link type is going to play a role when you're talking about heat aging. When you're using polysulfidic bonds, which have that low bond energy, you're going to have poor heat resistance. But on the flip side there, if I go with a very strong cross-link density, like let's say peroxide cure, where you're going to have very strong, very rigid carbon-carbon bonds, then you're going to have better aging properties. So like I said, think of thermal stability as a chemical mechanism. Then you have the second mechanism, and this is really looking at thermal properties. And when we're talking about thermal properties, we're talking about more of a physical mechanism. And the two things that are going to lead to this physical mechanism, one is thermal conductivity, which is how well a compound can conduct heat. And then also thermal effusivity, which is going to look at how well a compound can exchange surface heat with its surroundings. And the things that are going to affect the physical mechanism are filler selection. So you have a chemical mechanism and then you have a physical mechanism. So now we're going to talk about what is heat dissipation. So rubber heat dissipation is the release of internal heat generated within a rubber material to the surrounding environment. And think about it, rubber is an insulative material, making it hard for heat to migrate and to dissipate on its own. So heat buildup can cause the rubber to prematurely age, soften, or even fail. And to make a rubber compound have heat dissipative properties, you must add materials that are thermally conductive. And these are going to be thermally conductive fillers. So next we're going to talk about the heat dissipation theory. So fillers influence thermal conductivity through particle aspect ratio. And when you think about the aspect ratio of a particle, what you're actually talking about is the ratio of the length of the particle to its diameter. And the higher the aspect ratio, normally the more thermally conductive a filler will be. So you're not only looking at just aspect ratio, but you're also looking at phonon mobility. So phonons are the collective vibration of atoms in solid objects. And these atomic vibrations occur in waves and produce the thermal transfer of energy, heat from one region to another. So when you're talking about heat dissipation, as a compound is sitting there and it's building heat, what you want it to do is be able to dissipate it out into the surrounding environment. The more heat it can dissipate, the more protection you're going to give to your polymer compound. So now we're going to talk about fillers that actually promote heat dissipation. And the first one is zinc oxide. And most people don't think of zinc oxide as an actual filler, but if you go back to the onset of the industrialization of the rubber industry, zinc oxide was the original filler used. So if you go back to the beginning of the automotive industry, tires were actually white because the first filler used was actually zinc oxide. However, zinc oxide does not have the same reinforcement properties as other sorts of fillers. So it lost its filler status due to that low reinforcement and its very high specific gravity with the introduction of furnace carbon blacks. Now, zinc oxide is used in conjunction with stearic acid to activate sulfur cure. So normally you're going to have it in a rubber compound at less than 5 pHr, which is going to be anywhere probably from 2 to 3% of your rubber compound. Now, zinc oxide has what is called an equidimensional aspect ratio. So equidimensional just means that the length of the particle is the same as the diameter. And it's a fairly boring aspect ratio. And that is not what is giving it its high thermal conductivity. Its thermal conductivity is coming from the crystalline quartzite structure that it has. And as I mentioned, most people think, well, zinc oxide's just a filler, or it's just an activator, and it was a filler a long time ago. But I've been in the rubber industry for 29 years, and one thing I can tell you is that every peroxide cured compound I have ever seen has zinc oxide in it. And you have to wonder why, because you do not need zinc oxide to activate a peroxide cure. It's only going to activate a sulfur cure. The reason why that zinc oxide is in there is because it's going to improve heat resistance, and it does that through thermal conductivity. So the second filler we're actually going to talk about today is graphite. So graphite is traditionally used in the rubber industry to provide some form of lubricity. And it has a very platy aspect ratio. So what that means is that the particle is actually long and it's flat. And this long flat particle helps graphite to align in a compound where particles can touch, providing a thermally conductive network throughout the compound. The third filler is graphene, and its particle is a flat two-dimensional sheet resembling a cross-section of a honeycomb, and it has a very high aspect ratio. And this two-dimensional structure is what gives graphene its high thermal conductivity. And then the last filler we're going to talk about today is carbon nanotubes. And as the name states, the particles have a long tubular structure, and this tubular structure provides high aspect ratio, and it has high thermal conductivity because of the rigid carbon-carbon bonds and ordered atomic structure, allowing for high phonon mobility. So I wanted to put a chart together to actually do a comparison of thermal conductivity of different fillers and also polymer on its own carbon black, and silica. So carbon black and silica are being added because when you think about a tire tread compound, those are the standard fillers that are normally used. Normally you have about 15 parts of carbon black and about 60 to 65 parts of a precipitated silica. And so I wasn't able to get the exact thermal conductivity for each of the exact fillers trade names that we used. So I used my good friend ChatGPT, and I was able to pull up some very basic ballpark thermal conductivity. So if you look here, you can see polymer, as you would expect. It has very low thermal conductivity, and this is because it does not conduct heat very well. Carbon black, you can see, is a little bit higher, but not that much higher than the polymer. Silica is very similar to the carbon black. So traditionally, what goes into a tire tread compound is not very high thermal conductivity. So now let's look at the other fillers that we're going to look at in our study. So you can see zinc oxide has quite a bit higher thermal conductivity than the carbon black or the silica. Graphite is fairly similar to the zinc oxide. And then you see the graphene is much higher, and so are the carbon nanotubes. The one thing to keep in mind when I did look these up on ChatGPT, one of the things that I specifically asked for when I was talking about the thermal conductivity for graphene and carbon nanotubes was I asked for what they are in the ground state, not in the neat state. And I did this on purpose because to get them into a rubber compound, I have to mechanically break them down somewhat and disperse them in the polymer. So that's why these numbers might be less than what you would expect, what you would normally expect for graphene and carbon nanotubes. But like I said, I wanted to show what it would actually be within a rubber compound. So just to kind of give you a very generalized chart of what the different fillers look like that we're talking about. So now let's get into our experiment. So as I mentioned earlier, we're going to replace low levels of silica with thermally conductive fillers in a passenger tire tread formulation. And then we're going to do a variety of different testing. So I'm going to show you the formulations that we ran. We'll talk a little bit about the MDR rheology, look at unaged physicals, heat age physicals, rotary drum abrasion, which is your basic DIN abrasion, your dissipator, and then we'll also look at some thermal conductivity data as well. So first of all, these are the formulas that we ran, and this is just a very standard passenger tire tread formula. And you can see that our main filler here is our silica with 15 parts of carbon black. And so what we did is we replaced low levels of the silica with a more thermally conductive filler. So we replaced 3 parts of silica with 7 parts of a standard zinc oxide, because in our control we had 3, so we moved up to 10. Then we actually increased the level up to 15 parts. And then we went back down to our 7 parts, but here we're looking at a high surface area zinc oxide, so something that's a little bit more active. And then we looked at graphite, where we replaced 3 parts of silica with 10 parts of graphite. And then when we did graphene, we replaced 3 parts of silica with 5 parts of graphene. And in the carbon nanotube, we used a functionalized carbon nanotube. We actually replaced 5 parts of silica with 3 parts of the functionalized carbon nanotubes. And as a passenger tire tread formula, there are 3-pass mixed, and we did this in a 1.6 liter BR Banbury. So let's look at our our MDR rheology real quick, ASTM D5289. And we're going to talk about some of the things that we found, that some of it's surprising, some of it isn't. But as your zinc oxide level or your surface area of the zinc oxide level increased, the minimum and the maximum torque decreased, which was a little bit surprising because since zinc oxide is an activator, you would have expected maybe the maximum torque to go up a little bit. You also saw the scorch and the cure time actually lengthened. Once again, that was a little bit surprising because you would think, well, I should be activating my cure more, and we really didn't see that. Now with the graphite, it actually lowered the maximum torque and the minimum torque, decreased the cure time, and increased the scorch safety. And this I would actually expect because graphite, as I mentioned, is used to provide lubricity. So basically it's in there acting as a process aid. So I would expect my minimum and maximum torque to go down a little bit and for me to have a little bit better scorch safety because of that. So when you're talking about the graphene had higher maximum and minimum torque, and I would expect this. It also had faster cure time and increased scorch time as well. So that one seemed to run fairly normal with the exception of the scorch time. I would have expected it to be faster, not for it to be slower. The functionalized carbon nanotube had similar minimum and maximum torque as the control, so you really saw no real difference there. And it also had longer cure and scorch times as well. So that one was a little surprising. So now let's look at our unaged physicals per ASTM D412. So if I'm looking at my ultimate tensile properties, what you will see is with a increasing medium surface area zinc oxide, it was pretty much the same as the control. As I kept increasing my zinc oxide, my tensile properties increased. And really going to a higher surface area, zinc oxide really made no change in my tensile. Graphite was pretty much the same as the control, a little bit lower, and you really saw no difference with the graphene or the functionalized carbon nanotube. So now if I look at my ultimate elongation, here you will see that zinc oxide increased my elongation, and it increased it even more as I increased the level of zinc oxide. You really saw just a small drop off as I increased my surface area. Graphite is very similar to the control, as is the graphene and the functionalized carbon nanotubes. So far with our carbon-based thermally conductive fillers, you're not seeing much change here. Now, if we get into our modulus properties, so we looked at each side of the spectrum. So we looked at 50% modulus and 300% modulus. So the first graph here, looking at 50% modulus, you can see that you see very little difference with the zinc oxide. They're very similar to the control. The graphite actually saw a slight increase in 50% modulus. The graphene saw no change from the control, but you can see a huge increase in the 50% modulus with the functionalized carbon nanotube. It is over double what the actual control is. And that's interesting because you saw such an increase in modulus, but if I go back to the last slide, you didn't see a change in elongation or tensile properties. So that's pretty interesting with your functionalized carbon nanotube. So if I look at my 300% modulus, so now I'm looking at high modulus at elongation, you can see from my control, the addition of zinc oxide dropped my 300% modulus. Graphene and the graphite reduced it as well. Graphene was very similar, but you're still seeing higher 300% modulus with the functionalized carbon nanotube. So like I said, it's really interesting what you're seeing with the functionalized carbon nanotube because you're seeing higher stiffness, but you're seeing similar tensile and similar elongation. So now let's look at some of our aging properties. So when we heat age these, we did this for 70 hours at 70 degrees Celsius. And here we're looking at the percent change after heat aging. And you can see our control, you had a positive change of 10%. So my tensile properties actually increased. But you can see that by adding a little bit of thermally conductive filler, you can see that you actually reduced your change in age tensile properties by half. And this is all happening because you're actually dissipating heat and it is improving your change, and it's after heat aging, and it's making the compound more stable. And you actually see that your high surface area zinc oxide and your graphene had the least amount of change. So now if you look at your heat aged elongation change, here what you're seeing is your control had a positive change of like 22%. So what you're seeing, if the elongation is going up, then that tells me my compound is softening more than likely. And you can see that you have almost a 4-time reduction in your heat aged elongation change just by adding some thermally conductive filler to replace some of the silica in your actual tire tread formulation. And here what you will see is that your higher levels of zinc oxide and your functionalized carbon nanotube had the least amount of change. So we also looked at heat age 50% modulus change, and most of the time nobody ever looks at modulus change when you're talking about heat age. But when I think about a tire and I think about a tread, like I said, I need something that's going to be very, very durable, and it's going to have good abrasion resistance. And abrasion resistance is going to go along with stiffness. Stiffness is my modulus. So if my heat age 50% modulus is changing a lot, then over time, what's going to happen is as my compound softens, my abrasion resistance is going to get worse. So 50% modulus is a good indicator of how the material is going to soften and how that's going to impact your abrasion resistance over time. So if I look at my control here, you can see I lost 20% of my 50% modulus. So my compound is softening quite a bit. And then what you see here is that your higher level of zinc oxide or your highest surface area zinc oxide and the functionalized carbon nanotube had the least amount of change. So ultimately, those 3 fillers are at those levels, and those types are making my compound more thermally stable. But remember how I said stiffness is going to relate back to our abrasion resistance. So when we're looking at the rotary drum abrasion resistance, here we're looking at abrasion loss. So what that means is that a lower number is going to equal better abrasion resistance. And if I look here, I see the same trend. I see my higher level of zinc, my high surface activity zinc, and my functionalized carbon nanotube have the best or the least amount of abrasion loss or the best abrasion resistance compared to all of the other materials. And so once again, I thought this was a very neat correlation. And here you're actually seeing that with all of the compounds, you saw a reduction in abrasion loss with the exception of the graphite and the graphene. And so we wanted to kind of look in to see, okay, well, why do the graphite and why do the graphene not really follow the same linear scenario that we're seeing with the other fillers? So one of the first things we wanted to look at is dispersion properties. So most of my compounds had very good dispersion properties. However, you can see the graphite had the worst dispersion properties. And after looking at the data and thinking about it, it actually made sense to us, because if you think about it, because graphite is a lubricant, when you're adding it in a rubber compound, you're going to basically reduce the viscosity of the bulk of the material in the mixer, which is going to reduce your shear properties. Plus, because it is a lubricant, you're going to have a lot of slippage within the mixer as well. And so I don't think what you're seeing here is particularly poor dispersion of graphite, because there's a small amount of it in there. What I think happened is because the graphite is acting as a lubricant, what you're seeing is poor dispersion of the carbon black and poor dispersion of the filler. And anybody who's ever done an abrasion test before, if you have poor dispersion, that's automatically going to equal poor abrasion resistance, because as you have something running against your sample, basically rubbing against it, as it hits those undispersed particles, you're going to have more chunking out, which is going to be more loss. So interestingly enough, you don't see that with the graphene. So dispersion does not explain why the graphene isn't actually giving us better abrasion resistance. I will say it's interesting that the functionalized carbon nanotube also had poorer dispersion properties than all of the other batches, but thus far has actually tested out really well. And I think this is part and parcel to how a carbon nanotube actually works. If you were to disperse it down and get it dispersed very well, I think you would ruin all of the properties you're hoping to get from that carbon nanotube if you actually completely destroyed the tubular structure. So I think you always are going to want some level of poor dispersion with the functionalized carbon nanotube to get the desired properties that you need to increase modulus and to improve your abrasion resistance. So now we looked at thermal conductivity. So I had to break these out into two different slides, and the reason being is because the functionalized carbon nanotube had such high thermal conductivity that I could not see nuances in the other batches. So the first slide here with most of our fillers, you can see a slight increase in thermal conductivity with the zinc oxide, but you're really seeing not a real difference between surface activity or even how much you're putting in. In fact, as you increase the level, you see a little bit of a drop off, but that could just be a little bit of uncertainty in the test. And then you do also see higher thermal conductivity with the graphite and the graphene. And the graphite, that one makes sense because we saw it had better aging, but you're not really, and we know that the poor dispersion is probably what caused the poor abrasion resistance, but you're still seeing high thermal conductivity from the graphene, and you were seeing good dispersion properties. So if I had to guess why the graphene did not give us better abrasion resistance, we did not use a functionalized or a treated graphene. And graphene in and of itself does not have high surface activity, so it's not going to give good polymer filler interaction. So what that means is that it's incorporated in the compound, but I don't necessarily think it is built up into the polymer backbone and reinforcing the compound. So I'm still getting high thermal conductivity, and I'm still getting good heat resistance because it's there. But the reason why it's not helping the abrasion resistance, like I said, is because I think it just doesn't have a lot of affinity for the polymer because it's not treated. So if I look at my functionalized carbon nanotube, you can see that I have much higher thermal conductivity than all of the other fillers. We also looked at thermal effusivity, and once again had to break it out into two charts because the functionalized carbon nanotube was so much higher. And you really don't see a difference with the zinc oxide. So you do see a bump in thermal conductivity. So it's able to move heat throughout the part. But as far as thermal effusivity goes, it's not really able to dissipate it really well from the surface. But you are seeing higher thermal effusivity with your carbon-based ones, your graphite and your graphene, and then ultimately much higher with the functionalized carbon nanotube. So in conclusion, heat age 50% modulus had a similar trend to abrasion resistance when using your thermally conductive fillers. All the fillers drastically improve the heat resistance of the tire tread compound when replacing low levels of silica. This is due to the thermal conductivity of the fillers used to dissipate heat, improving long-term aging performance. The zinc oxide also improved abrasion resistance, even though it did not have much impact on thermal effusivity, but we did see a slight bump with thermal conductivity. The graphite had the worst dispersion properties due to its natural lubricity, reducing the shear forces in the mixer, leading to poor dispersion of carbon black and silica. This poor dispersion of fillers in the graphite batch caused the poor abrasion resistance. The graphene saw no improvements in abrasion resistance, even though it had increased thermal conductivity and heat resistance. This is more than likely due because it has low surface activity or low polymer filler interaction. So the functionalized carbon nanotube improved heat resistance and improved abrasion resistance by 25%. However, the abrasion resistance would have also been influenced by the high modulus properties. So do you remember at one of the beginning slides when we first started looking at data that 50% modulus was almost double what the control was by adding, I think it's like 2% or a little bit under 2% carbon nanotubes. So that is also influencing the properties. And that's a good thing because what that means is you could probably use less of that functionalized carbon nanotubes. So just a couple of acknowledgements. I would like to thank my colleagues who also participated in this work with Barry Palmer Jr., Nathan Samples, Todd Romine, Dave Hauk, Cheryl Wood, and David Warner. And I would just like to give a shout out to my company real quick, ARDL, also known as Akron Rubber Development Laboratories, and we're an independent testing and development services for all your rubber and plastic needs. And I would like to thank everybody for attending and let us know if you have any questions.
Awesome. Thank you very much, Nikki. So for the folks here, we're just going to go into a quick little outro just to get things wrapped up here today. And just as a reminder, if you did have any questions about today's session, type those into the chat to the Q&A feature there, and we will be addressing those here in the next few minutes. So just on the way out here, I will make note if you're looking to maybe explore some similar content or kind of where to find that on our website. Again, all of these webinars are recorded. You can take a look at those. There's also a tech library, so many of the publications and papers that are referenced in some of these talks are also stored there. You can find the according links. Wanted to make note of some upcoming webinars for the rest of the month of October. Next week, October 21st, we're going to be joined by some researchers from Penn taking a look at thermal conductivity testing for building thermal mass performance and emission saving. And then later on in the month, the final webinar this month will be a DMA-focused webinar with Dr. Richard Pazur. So if those are of interest, the registration links are available for those for the next couple weeks. So on the way out, also just making note that, of course, today we focused a lot, on the thermal management side of things, reference to thermal conductivity. At C-Therm, we are partnered with both Rigaku and Metrobib for their line of thermal analysis and mechanical analysis testing, respectively, as well as our thermal analysis labs group, which offers testing services for all of the methods that we have, all the transient methods on Trident, as well as some others that exist in industry. If you'd like to learn more, maybe do a little bit more of a deep dive on some applications that you're working on or some specific samples that you're looking to test, how to go about doing that. We do offer free technical consultations. You'd be able to come in, do a little one-on-one where we learn about your application, try to propose some testing options, both from capital equipment like instrumentation side and also for our testing services. If what you've seen is of interest and maybe you're just looking for some budgetary information, you can also certainly request a quote. I'm happy to provide those, again, whether it's for an instrument or for testing. Someone from the team will be happy to touch base and get one of those sent over to you. If anyone on the line is from an academic institution, I will make note of our academic support program for our Trident product. So just as a reminder, if you are looking to bring some testing capabilities in-house, you're at a university, these, discounts and offers that are available to our academic members. Definitely feel free to reference this in your reach out to us. We're happy to provide some additional information. My last kind of ask here is for folks, if you aren't doing so already, give us a follow on LinkedIn. This is where we post all of our latest and greatest content, whether it's upcoming collaboration work, webinars, blog pieces, whatever that may be. You can find all of that first on LinkedIn. And with that, that brings us to the end of today's session. For the folks that are dropping off, thank you for joining us here today. And also thank you to Nikki for taking us through that content today. Just as a reminder for the folks that do want to stick around, we're going to end the official recording at this point, but then we'll go into the Q&A section. So stick around for that if that's of interest. All right.